Section 5 of The Einstein Theory of Relativity by Hendrik A. Lorentz. New system or coordinates. What way Einstein had to follow is now apparent. He must, this hardly needs to be said, in calculating definite particular cases, make use of a chosen system of coordinates. But as he had no means of limiting his choice beforehand and in general, he had to reserve full liberty of action in this respect. Therefore, he made it his aim so to arrange the theory that, no matter how the choice was made, the phenomena of gravitation, so far as its effects and its stimulation by the attracting bodies are concerned, may always be described in the same way. That is, through comparisons of the same general form, as we again and again give certain values to the numbers that mark the sphere of gravitation. For the sake of simplification, I here disregard the fact that Einstein desires that also the way in which time is measured and represented by figures shall have no influence upon the central value of the comparisons. Whether this aim could be attained was a question of mathematical inquiry. It really was attained, remarkably enough, and, we may say, to the surprise of Einstein himself, although at the cost of considerable simplicity in the mathematical form. It appeared necessary for the fixation of the field of gravitation in one or the other point in space to introduce no fewer than 10 quantities in the place of the one that occurred in the example mentioned above. In this connection, it is of importance to note that when we exclude certain possibilities that would give rise to still greater intricacies, the form of comparison used by Einstein to present the theory is the only possible one. The principle of the freedom of choice in coordinates was the only one by which he needed to allow himself to be guided. Although thus there was no special effort made to reach a connection with the theory of Newton, it was evident, fortunately, at the end of the experiment that the connection existed. If we avail ourselves of the simplifying circumstance that the velocities of the heavenly bodies are slight in comparison with that of light, then we can deduce the theory of Newton from the new theory, the universal relativity theory, as it is called by Einstein. Thus, all the conclusions based upon the Newtonian theory hold good, as must naturally be required. But now we have got further along. The Newtonian theory can no longer be regarded as absolutely correct in all cases. There are slight deviations from it, which, although as a rule unnoticeable, once in a while fall within the range of observation. Now, there was a difficulty in the movement of the planet Mercury which could not be solved. Even after all the disturbances caused by the attraction of other planets had been taken into account, there remained an inexplicable phenomenon, that is, an extremely slow turning of the ellipses described by Mercury on its own plane. Leverrier had found that it amounted to 43 seconds a century. Einstein found that, according to his formulas, this movement must really amount to just that much. Thus, with a single blow, he solved one of the greatest puzzles of astronomy. Still more remarkable, because it has a bearing upon a phenomenon which formerly could not be imagined, is the confirmation of Einstein's prediction regarding the influence of gravitation upon the course of the rays of light. That such an influence must exist is taught by a simple examination. We have only to turn back for a moment to the following comparison in which we were just imagining ourselves to make our observations. It was noted that when the compartment is falling with the acceleration of 981, the phenomena therein will occur just as if there were no attraction of gravitation. We can then see an object, A stand still somewhere in open space. A projectile B can travel with constant speed along a horizontal line without varying from it in the slightest. A ray of light can do the same. Everybody will admit that in each case, if there is no gravitation, light will certainly extend itself in a rectilinear way. If we limit the light to a flicker of the slightest duration, so that only a little bit, c, of a ray of light arises, or if we fix our attention upon a single vibration of light, c, while we on the other hand give to the projectile B a speed equal to that of light, then we can conclude that B and C in their continued motion can always remain next to each other. Now, if we watch all this, not from the movable compartment, but from a place on the earth, then we shall note the usual falling movement of object A, which shows us that we have to deal with a sphere of gravitation. The projectile B will, in a bent path, vary more and more from a horizontal straight line, and the light will do the same, because if we observe the movements from another standpoint, this can have no effect upon the remaining next to each other of B and C. End of section 5.